generate the solid? These are questions we must resolve in the next few lectures. So the primary thermodynamic metric for how CO2 absorbs on a surface is called an isotherm. And let's talk a little bit about what that looks like. So here I have a cartoon showing a porous solid. And here I have a gas above it, and it has carbon dioxide absorbing and nitrogen which does not absorb. And it is at thermodynamic equilibrium. And I'm able to express for absorption, you remember, the amount in the material as a function of pressure. That was for absorption. They had these Henry law coefficients. And it turns out for isotherms, we just flip these around and we get the same kind of information. Here's the pressure of CO2 here, and here's the amount on the surface of the powder. The difference, the reason in liquid phase they use these graphs, and in solid phase they use those, is historical. It's nonsensical to students, and it frustrates them. Okay, so I was frustrated too when I was a student. So we've learned to deal with it, yes? And you'll recognize there's a region where it looks very, very linear, and there's a region where it levels off. So as I increase the pressure, I reach a point where no more CO2 goes on the surface. The surface is said to be saturated. So this is the moles per mass of absorbent. So how do I figure out what that number is? I need some numbers. A fractional loading, that is how many of these sites are occupied by CO2. I have 1, 2, 3, 4, 5, 6, 7 sites here. 3 are occupied, therefore the loading is 3/7 in this cartoon. I have desorption then from the surface back to the gas, and its rate is proportional to the number of sites that are occupied. A little phenomenological equation. There's the maximum number, there's the concentration. I also have adsorption now from the gas back onto the surface, and that is proportional to the number of available sites, which is 1 minus the ones that are already absorbed. And so I have a different equation that looks at the rate at which species in the gas phase and the empty sites sort of react with each other. At equilibrium, these two rates are equal, and then I just make the definition of this number B, and I get that the loading of my surface depends on pressure in this way, P over 1 plus P with a constant in front of it. This is a very, very famous equation. It's called a Langmuir equation. Probably many of you have heard of Irving Langmuir, who won the Nobel Prize for the surface chemistry. And so what this equation looks like, if you plot it with your computer, is that as pressure increases, you reach a maximum value in which all the surface sites are covered, the so-called Langmuir isotherm, as again I showed again here. So in the limit, as we get to lower and lower pressure, say down here, we can look at this equation, we can take the limits, and we see that there's a constant that represents the relationship between sigma max and pressure. So it's linear. So Henry's law holds for low pressures. It's a different Henry's law constant. And the previous video made mention of you that when you look at Henry's law constants in the literature, you have to look very carefully at their units, because the units depend really on how it's practiced. But the idea is very simple, that the amount on the surface is linear with pressure with a constant, which can be calculated from fundamentals of first principles. It can be measured, and once measured and calculated, can be used for design. And there's the slope k sub h right there. There's another way to measure the surface area, or another family of isotherms, named after Brunauer, Emmett, and Teller. They published this paper in 1938. It's really a tour de force in physical chemistry. Students of physical chemistry will recognize this man's name. His name is Edward Teller. He was the inventor of the hydrogen bomb, right in the post-World War II era. So what you're asking yourself, why is a hydrogen bomb guy on this paper with 2 chemists? The answer is the chemists couldn't solve the math. And they got together with their friend who they knew, Edward Teller, and Teller helped them figure out the math problem. And so, by the way, if you go and look at this original paper, and students of physical chemistry, I would encourage you to do so, you'll discover that it is an extremely sophisticated piece of work. So, not assumed. So here's a cartoon here that shows a cartoon of a surface, and here you see molecules absorbing. Here you see a monolayer, and here you see multi-layers start to forming with some condensation occurring in these very narrow areas. And if you look at how much is absorbed as a function of pressure, you get these isotherms that look something like this. And these are so-called BET isotherms. And there's a hysteresis in these isotherms. That is to say, the amount of gas on the surface depends on whether you're increasing or decreasing the pressure, and that tells you a great deal about pore size, volume, and area. The mathematics of which we really don't want to go into. We just want to know a little bit about how this looks. And here's a cute cartoon. I forgot to delete the annoying music, but nevertheless, excuse me, you can see the adsorption process taking place, some condensation into these capillaries. So there's a whole family of isotherms that are associated with these processes, the so-called family tree of isotherms. There are isotherms that are associated with weak forces between the adsorbate and the adsorbing molecule, and so forth and so on. If you're a sophisticate in the area of adsorption and you measure these isotherms, and if you say to somebody, I have a type 3 isotherm, they know instantly what you mean. They know that you mean this particular kind of isotherm, and they understand the relationship between the adsorbate and the surface and the adsorbate and itself. So what about mixtures? Isotherms for mixtures. So if we're going to measure the capacity of a powder for absorbing CO2 from a CO2 nitrogen mixture, we need to know how nitrogen and CO2 adsorb. And so again, we're going to look at partial pressure, your equation from freshman chemistry, mole fraction, partial pressure, pressure total. And let's say for carbon and nitrogen, we have these two species. If the adsorption of each component is independent, then the total surface sites filled are just those filled with carbon and those filled with nitrogen. You can rearrange those, put in the Langmuirian isotherms, use the linear relationship at low pressure, and you just have a simple additive properties for the adsorption processes. This works pretty well some of the time. Certainly a good way to start an analysis. You can look at the selectivity of these particular materials by looking at how much CO2 is on the surface versus nitrogen at a given pressure. And if you take the ratio of those numbers, that turns out to be the ratio of the Henry law coefficients. So the ratio of these two slopes tells you how selective the surface is for CO2 over nitrogen. And just to ground you a little bit, in the design of materials for carbon capture with a flue gas via adsorption, you need a factor of at least 20 difference between CO2 and nitrogen in order to have a viable process. And that turns out to be relatively straightforward to imagine and accomplish. There are better theories. If you're a chemical engineer, you would learn about these. And we don't need to say any more other than the fact that there are more sophisticated theories. So, yeah, I hear what you're saying. So I'm getting the message here that Professor Reimer needs to get out quickly. So we'll pick up on this next time, and I'll adjust a little bit the next two topics so that next time we're 3 hours, you and I are together. Yeah, it's very hard, okay? But we'll try to endure. So I'll see you tomorrow, and there'll be no short shrift tomorrow. Okay, see you then.